Good afternoon, and welcome to the Society of Wetland Scientists May 2020 webinar titled Before the Ghosts Appear, Identifying the Effects of Chronic Saltwater Intrusion on Coastal Floodplain Swamps Using Remote Sensing. Today our presenter will be Elliot White, Jr., PhD. My name is Louis Mantini, and I'm pleased to moderate this webinar. And on behalf of the Society, I hope you are all doing well during this global pandemic. For those of you not familiar with our webinar series, all monthly webinars are complimentary to SWS members and are usually held on the third Thursday of the month. However, once every quarter, webinars are offered for free to non-members and the public. As you can see on this listing of our upcoming webinars, we have both our regular webinar series in English and also have quarterly webinars offered in Spanish. Our next free webinar will be held in July and will be presented by our 2019 Wetland Ambassador, Priyanka Sarkar from Assam University in India, and her mentor, Elizabeth Watson from Drexel University in Philadelphia, Pennsylvania. We also have 4 sponsors this year, new sponsors for our SWS webinar series, and they include Water Resources, Hydrology and Hydraulics Education, which is a nonprofit that shares information on water resources, hydrologic and hydraulic engineering to help educate and build a better tomorrow. Please visit their Facebook page and like them and follow them. We also have the Whittington Group, which is a natural resource consulting firm that balances regulatory compliance with sound ecological management. And certainly you've heard of In Situ. They specialize in the provision of sampling, monitoring and measuring equipment and services for the use in a wide variety of groundwater and surface water applications, and WildNote, which is a field data collection app for environmental professionals used for environmental compliance monitoring, ecological restoration, and wetland and cultural resource management. So I'd also like to mention that this webinar has been pre-approved by the SWS Professional Certification Program and is applicable for continuing education credits. These credits can be applied to your professional wetland scientist certification or renewal, or other certifications for that matter. Participation certificates are available through an automated process where you will receive an email from our Managing Director, Michelle Chosek, about 1 day after the webinar. Check your spam email if you don't see it. These certificates are free to SWS members and are available to non-members for a nominal fee of $20. Participation certificates are also available for those who watch webinar recordings, which can be found on our past webinars page or YouTube channel, which, by the way, has become quite popular, particularly during this pandemic. And I recommend you sign up for that YouTube directly. So, I'd like to go over just a few housekeeping items before we begin. We have now gone to the Zoom format, and this is our maiden voyage of sorts. So as you see in this example panel here, all the participants are muted. There's a question and answer and a chat button on the bottom of the page. Please enter all of your question and answers in the Q&A button, and those will be directed to me, where we will share with Elliot at the end of his presentation. Panelists are usually located on the top right-hand corner of the panel, and as you can see in the image, we have Kimberly Ponzio on the left. She's our past SWS president and current committee chair, and the star of the show, Elliot White, on the right-hand side. So, with that out of the way, I'd like to introduce to you Elliot. And Tony, could you advance the slide? I'm going to stop sharing. I'm not getting a response here.
Hello, everyone.
Unshare, stop sharing, and then Elliot will be able to take over.
Okay.
Perfect.
Well, let me please introduce you, Elliot, because it's my distinct pleasure to let you know that Elliot is a research associate in the Environmental Sciences Department at the University of Virginia. Elliot's research seeks to capture and understand the effects of sea level rise and saltwater intrusion on coastal wetlands across large geographic gradients. His current research efforts involve mapping loss and conversion of Atlantic coast and North Gulf of Mexico wetlands due to saltwater intrusion and sea level rise over the past 30 years. The next steps of his research will be finding vulnerable coastal wetlands and generating probability-driven maps of future wetland coverage. The goal of this research is to guide future research and conservationist efforts. Elliot's doctoral research sought to understand how coastal floodplain swamp, gaseous carbon flux, nitrogen storage, vegetative community structure and composition, and health shift with landward advance of riverine and groundwater isohalines. Elliot's doctoral research covered a large geographic range across the northern Gulf of Mexico and Florida, Louisiana, and Texas. He received his PhD in environmental engineering sciences from the University of Florida in 2019 and his BS in biology and animal ecology from Iowa State in 2015. And with that, I'd like to turn this over to Elliot.
Thank you for that introduction, Lewis. Hello, everyone, and I'm happy to have you all here for me to present some of my dissertation research, one of the chapters of my dissertation research. And I'd like to thank my former advisor, David Kaplan, for always being a great teacher and guider and research mentor. So, as Lewis mentioned, this presentation is going to be about trying to assess the health of coastal floodplain swamps across the northern Gulf of Mexico. And this particular research idea uses remote sensing to tackle those issues instead of more traditional methods, ecological methods, which we've used for decades at this point. So I'll first start with the take-home message of this presentation. And those are that remote sensing data can be used to identify swamps which are stressed by saltwater. The outcomes or the effect of saltwater intrusion is much easier to detect in swamps than the actual process of saltwater intrusion. And that remote sensing can be used for both monitoring and exploration as long as you have adequate local knowledge of the issue. And as I said before, this is kind of one slice of my dissertation. And as Lewis pointed out, I focus on several other things, but this particular chapter, I'm looking at the coastal landscape with a particular emphasis on swamps and using remote sensing to understand how their health and population dynamics change with the advancement of saline water. So just for contextual reasons, I think it's important to remind everyone that the coastal wetland mosaic is not one type of community. It's represented by a different amount of vegetative communities, which are themselves dispersed upon abiotic gradients, which include hydroperiod salinity and nutrient gradients. The differences in these gradients greatly impact the ecosystem structure and function of any wetland coastal area. Coastal floodplain swamps in particular are prevalent along the southeastern United States, from Texas to Florida up to Virginia, Maryland area. It's estimated that they provide about $25,000 per hectare per year worth of ecosystem services. And those ecosystem services are include nutrient removal, storm surge attenuation, and carbon sequestration. And it's important that their landscape position allows them to provide these ecosystem services, but on the other hand, their landscape positioning makes them very vulnerable to saltwater intrusion. Sea level rise and saltwater intrusion are well-known risk factors for any coastal wetland vegetation, particularly those that are freshwater. Saltwater intrusion is particularly important for swamps because the current rate of soil accretion for swamps is unable to keep pace with the current rates of sea level rise, as shown by Chris Kraft on work in Georgia and South Carolina. Additionally, saltwater intrusion is a well-documented threat to coastal floodplain swamps. And it's important to understand the drivers of saltwater intrusion themselves so that we have a better understanding of where we should investigate and where we should focus our attention. Drivers can be both natural and anthropogenic, with natural drivers being varying over both a temporal and a spatial scale. And these drivers include natural phenomena like hurricane, drought, large-scale climate oscillations like El Nino and natural sea level rise. In addition, we have anthropogenic sea level rise, which varies across a shorter temporal scale and a smaller regional scale. And those include human-driven activity like land drainage for agriculture, for example, groundwater extraction for municipal and industrial use, channelization of rivers or river modifications. All of these different, both natural and anthropogenic phenomenon help to drive saltwater intrusion further inland and exacerbate any existing issues. And so looking at these pictures, you can kind of see a stepwise change in the salinization of a swamp and the effects that we see. So in a freshwater or in a swamp that is where the hydrology is of fresh water, when you look up at the canopy, you see a fairly closed canopy and a really shady understory, dominated largely by bald cypress or different fraxinus or tupelo species, Nyssa species. However, as the groundwater salinity starts to increase, you'll notice a shift in the canopy. So you'll have fewer trees. The trees that are dead will be start to appear like they're dying. And then there is understory vegetation that will also start to shift. So in this particular picture, it was taken in a swamp in Beaumont, Texas. The brown vegetation are dying cattail and the green vegetation are saltgrass. Saltgrass is very saltwater tolerant, whereas cattail is much more limited in their saltwater tolerance. And then this last picture on the right is a picture from in the same kind of general area of the swamp where sawgrass is much more dominant in terms of vegetation, and the canopy trees are few and far in between. And this is not just a problem that's isolated to Texas, as these three pictures come from Texas. It's a problem that can be found in Louisiana, Mississippi, Alabama, Florida, all across the northern Gulf of Mexico and across the Atlantic coast as well. And this, for me, prompts the need for a region-wide understanding of the effects of saltwater intrusion. And I am very much new to the game when looking at this problem. There's a large body of literature that has sought to understand this issue. And these different case studies have looked at this issue in different places, allowing us to draw a higher level understanding of these effects across this large gradient. However, many of these studies fail, or not fail, I should say, but you can't scale up their local results to a more global understanding, which is something that I intend to do. But as I said, there's a large body of literature that has focused on this issue. And in addition, there's growing mainstream attention for ghost forests, or forests that are still standing, or the trunks are still standing, but they're dead. So it resembles what once was. So there's been media coverage by Science Friday, by New York Times, and several outlets over the past 5 years that have really put a lot of focus on this particular issue, with this big headline from CBS: Ghost forests, what they are and why they're becoming more common. And I wish I had seen this headline, because maybe I would have stolen it for my dissertation title, because it's pretty much what I did. So as I address concerning the literature and previous work that's been done, there are some challenges that come with using our more traditional ecological methods to address this issue at a large scale. So one, just being the amount of time that's involved using traditional ecological methods, where you have to have maybe 3 to 5 years of, on the ground, 3 to 5 years of on the ground research to really get a good understanding of what's going on. You need money invested for a long amount of time to do that. And funding is something that's very fickle at times when it comes to research. You need permits, which depending on the administration may be hard to get. You also need the right amount of tools and maintenance for those tools and equipment. You need people who are interested in what you're doing and willing to work from you. You have to maintain your interest over a long period of time. And as I hit on before, your results in one location in one state may not scale up to a regional understanding. So all of these are challenges that are always present for traditional ecological methods, and we find ways to work around them. But these are challenges that exist nonetheless that make research harder at times. So my way to address this issue was by using remote sensing to tackle it. Remote sensing allows us to avoid many of these challenges. It can be visible when trying to examine, or it can be beneficial when trying to examine processes that are very visible to us with our naked eye. And it allows us to apply a method that's easily scalable because we don't have to go out into the field every time to apply this method in a new location. We just relocate where we're zooming in on a map. And in particular, I use Google Earth Engine because I had not done remote sensing before and I needed a system that was fast and easy to learn. So that's the software that I chose to use for this research. In particular, detecting vegetative change. There's been a lot of research using remote sensing to detect change in vegetation, and those changes have been identified as like differences in vegetative structure, composition, and spatial distribution of vegetation. There are also a plethora of vegetation indices that exist, and many of these were designed with a particular research question in mind, but some are generalizable. I use EVI, the Advanced Vegetation Index, in order to address this issue. EVI in particular is sensitive to high biomass areas, so something like you would expect in a swamp or in a rainforest, and it corrects for aerosol scattering and some effects of background soil reflectance. So it gives us a more clear picture of just the reflectance of the vegetation, and it kind of mutes some of the extra information that you may get that could skew your results when you're analyzing and interpreting. So more specifically about swamps themselves, swamps are a mixture of needle and broadleaf canopy species. And as I mentioned earlier, those species are Taxodendisticum and several Nyssa and Fraxinus species that are intermixed throughout the canopy. They're characterized by yearly leaf senescence in the fall, and that senescence is driven by, or the timing of that senescence can vary with different abiotic factors, including flood depth, temperature, and salinity stress. Ground cover, importantly, is often very rare in these systems and sparse, and I'll talk about more why that's important on the next slide. And canopy species have a very limited tolerance to salinity, which is why saltwater intrusion into these areas is very important, or not very, why it's causes such damage for the vegetation that naturally exists there. So going in kind of with a general framework of how I started to approach this question, I have these idealized differences in coastal floodplain swamp health. So during the summer, if you're in a swamp that is healthy, it has plenty of fresh water, and you look up at the canopy, you should see something like this top image where the canopy is fairly closed, it's leafed out, and there's not a lot of sunlight penetrating through. Whereas if you're in an area where groundwater salinity is elevated above what the canopy species can handle, and in general in the literature, the tolerance for these canopy species for salinity is about 2 to 4 parts per thousand. And to put that in context, ocean water is about, on average, 30 to 35 parts per thousand, depending on where you are. So in that context, the groundwater salinity levels that they can handle is fairly low, but for them, 2 to 4 parts per thousand is really high. So when you're in an area where groundwater salinity is elevated for this system and you look up, you see large openings in the canopy, you see branches that are not fully leafed out, and there's a lot of light hitting the ground. And you can see that light difference here. So in this system, you have almost no understory vegetation present, a lot of shadows on the ground, whereas in this salt stress situation, you have a lot of understory herbaceous vegetation present, a lot of light penetrating to the ground, which allows these herbaceous understory vegetation to persist and proliferate. In the winter, because of this yearly leaf senescence, most of the canopy trees drop their leaves, which allows light to now penetrate into the understory. However, because this is something that happens on a yearly cycle, the understory vegetation is never really able to take hold in a freshwater system, in an upstream system, compared to a downstream system that is likely impacted by freshwater, where you have your leaves drop, but these vegetation are still able to persist. And the differences in the the phenological patterns over the course of the year, we can use that understanding to help us start to develop a question and hypotheses to use remote sensing to address this issue. So the overarching research question for this part of my dissertation was, how can remote sensing data be used to track the long-term impacts of saltwater intrusion on coastal floodplain freshwater swamps? So owing back to those differences that I just highlighted in the images, we can now take that conceptual understanding and start to put together some cartoon figures of how the remote sensing data should look given our conceptual understanding of these differences. So on this figure, you have EVI on the left and years or just time on the x-axis. And this blue line represents the long-term trend in EVI values at the upstream or freshwater site. So in the long term, if the system is healthy and is not experiencing any consistent drivers of change besides interannual or long-scale variation, you would expect EVI values to remain consistent, or maybe there may be some increase, maybe some slight decrease, but on average, it's going to be pretty consistent. And this squiggly line here represents kind of the variation from year to year. So you have growing season where you have the leaves fleshed out, then you have the dormant season where you have no leaves. So the EVI value is just a reflection of that change in leaf out, leaf on over the course of the year. Next, if you take an average year, you have that, that same shape. So during this period is when leaves are coming onto the trees. You have the growing season where it's fully leafed out, you're at maximum productivity of photosynthesis. And then you hit a point in the year where leaves start to fall off, and you have the dormant season where there's no leaves fleshed out. So your EVI value, once again, is going to follow the trend of the leaves in your system. And then the distribution of the EVI data will have somewhat of a bimodal distribution, because you have these two different modes, or these two different times of the year where most of your data points will fall. So you have your growing season, which is characterized by high EVI, so that maps to this point over here. And then you have your dormant season, which is characterized by low EVI, and that maps to this point. So an upstream or freshwater swamp should have a somewhat bimodal distribution going back to the phenological patterns over the course of the year. However, when you start to think about what does a downstream or an area that's likely impacted by saltwater intrusion, what type of patterns will those systems display? And in general, because we know the ecological effects of saltwater intrusion on swamps, we would expect that EVI values would start to decline over time due to the canopy trees being negatively impacted. And the vegetation that will take hold will have, in general, a lower EVI value than the canopy trees that should naturally be there. In an average year, the growing season values will be lower because there's less productivity, less reflectance in the leaves, and the dormant season values will be higher because there's understory vegetation instead of bare soil. So the understory vegetation is going to inflate the reflectance values and give you a higher EVI value. And the distribution will shift to the left. So you'll have generally lower EVI values, which you can see here if you take this average compared to that average. And the distribution should also approach a unimodal distribution, which once again, this looks more unimodal, or it has the values vary less around the mean than this distribution does. So taking these conceptual understandings a bit further, I developed a set of hypotheses that I intend to use in concert with one another. So if you take the EVI data and run it through all 8 of these hypotheses, or all, yes, 8 of these hypotheses, you should get an understanding of how saltwater intrusion is affecting your given swamps. So these first 2 hypotheses, which I won't go into detail because it's very wordy and it's something that is much easier to read, but these first 2 hypotheses try to statistically differentiate between an upstream or freshwater swamp compared to a downstream, potentially saltwater impacted swamps by comparing their distributions to one another and the location of their medians to one another. These next 3 hypotheses look to use long-term changes over time. So comparing the slopes of the different locations to one another to see if the slope of one is changing more rapidly than the slope of the other, for example. And then these last 4 hypotheses both rely on different parts of the distributions and the trends. So the first 3 of these 4 compare the growing season dynamics between the 2, the dormant season dynamics between the 2, and the ratio of those. And they also compare the ratio of the long-term slopes of the growing season, dormant season dynamics. So as I said, I won't step through each of these individually because it can get very wordy. So I will go over them in broad strokes in the results and get more specific about the hypotheses that were best supported or most supported across all sites. So a little more about the methods. As I mentioned previously, swamps are found across this entire North Gulf of Mexico gradient. I have sites along the Neches River near Beaumont, Texas. Beaumont is here. I have sites in Southeast Louisiana, so in the Atchafalaya River Basin and at Jean Lafitte National Historic Park. I have sites in the Big Bend area of Florida, and then sites along the Suwannee River. And the remote sensing workflow, so I use the MODIS Terra 500-meter surface reflectance data. I took that data and masked it for clouds, cloud shadows, and incomplete pixels so that the only data that I was getting is data that are the reflectance values of vegetation. I calculated EVI across each of my regions of interest and averaged those pixels together to get a single value per image per site. Create an image collection, and from that image collection, we're able to get basically 2, we can visualize or look at the data in 2 different ways. We can look at the data as a time series. So for each site, we would have a time series of data. And then for each site, we can also develop a distribution. So I'm going to take a quick break for some water. Okay. So I have the suite of hypotheses that I applied to the data in order to see if you're able to differentiate between a potentially saltwater stress site compared to a site that you know is receiving only fresh water. And in general, what we found was that across all sites, the hypotheses were supported 53% of the time, meaning that 53% of the time, if you apply all of these hypotheses, all 9 of these hypotheses, you're able to tell a saltwater stress site or potentially saltwater stress site apart from a upstream freshwater site, which is not very great. It's a little bit better than chance, so not what you're looking for in research. But when you look at the performance or the support of these hypotheses at each site individually, so if you look at the Suwannee River, for example, applying all of these hypotheses, they're able to differentiate between the 2 78% of the time. However, in Louisiana, for example, it only works 33% of the time. And when we look more closely, we can see that a subset of hypotheses actually had higher support across all the sites. So hypothesis 1, hypothesis 1B, hypothesis 3A, and hypothesis 3C, all were supported 75% or more across all 4 sites. Excuse me. Which means that if you apply those 4 hypotheses only, you're able to differentiate between a saltwater or potentially saltwater stress and freshwater site 81% of the time. And this is only using EVI data, not using any additional contextual information. And we have 2 locations in Florida. So in the Swanee and Big Bend area, those 4 hypotheses are supported 100% of the time. And the Neches River area, 75% of the time. And Southeast Louisiana is still the lowest at 50% of the time. And so next, I'll go into detail on the 4 hypotheses that were best supported across all sites, and try to link each or explain the ecological understanding and rationale of each of those hypotheses, and interpret those results for some of the locations. So, as I said, these 4 best performing sites tended to focus on differences in summary statistics, so differences in the median values or the distribution. However, the sites that failed to be supported across sites on average tend to focus on long-term statistical parameters like trends and slopes and linear regressions. So 5 of those 9 hypotheses focus on those, and those are the ones that failed to get more than 75% of support across all sites. So going back, we're going to step through the 4 hypotheses that perform best across all sites, and as I said, link those back to what we know to be true ecologically. So hypothesis H1A compared the median EVI values across sites. So we know that there's a reduction in primary production associated with saltwater intrusion. And this hypothesis basically looks at that. So the median EVI value is going to reflect the EVI value that is most common over a given time period. And if we understand that saltwater intrusion has a negative impact on EVI, on primary production, that's going to in turn have a negative impact on EVI. And that's where we get this difference that we're seeing supported across 3 of the 4 sites. So chronic stress leads to lower primary production. And as I said, EVI is going to reflect that trend. The place where this wasn't supported was Southeast Louisiana. And in particular, our site, so this site here in Jean Lafitte National Historic Park, was a site that we assumed to be experiencing the effects of saltwater intrusion. And I'll take a step back and say something that I should have mentioned earlier in the methods. At 7 of the 8 sites that I use in the study, there's sites that I've been to, and we have 4 years and more of groundwater salinity data. So the sites that I marked as saltwater intruded for the purposes of statistics are sites where I know the groundwater salinity for at least 4 years. And the one site where I don't have any groundwater salinity data is this site in the lower, in the Atchafalaya River Basin, but I use a CRIMS, the Louisiana Coastal Monitoring Network. There's a hydrology gauge at this site, so I was able to get hydrology and salinity information from that site. So for all of these sites, I do know the salinity information, which helps me understand the results that we're seeing. So back to this slide. So as I said, the EVI values for this site that we assume to be saltwater intrusion intruded were much higher than we would have expected, which owes to the reason that the hypothesis was not supported at this site. In addition, there's a proliferation of Tridacus subifera at this site, which may be inflating the EVI value outside of what we expected to be happening conceptually. And this area of the state is very hydrologically altered, which may be playing an important role in the EVI values that we're seeing here, because the EVI values may be askew from what you would expect to find ecologically. And the second hypothesis, this one was supported across all 4 sites. And this hypothesis, which compares the difference in EVI distributions, looks at the long-term change in seasonal patterns from year to year. So as I said before, a freshwater swamp should generally have a bimodal distribution due to having a stark difference in EVI values during the growing season compared to the dormant season. Whereas a site that's experiencing saltwater intrusion should have a distribution that skews more to the left, so lower values, and it should be more unimodal because there's a compression of the EVI values during the growing season compared to the dormant season. So this was supported across all sites. And there's also this third point that there may be subtle shifts in leaf emergence and senescence, which can play a role in that change in the distribution. However, I would like to say that the approach that I use here was not explicitly looking for a change in senescence or leaf emergence, but this is a ecological understanding that we have that may be playing a role in the data that we see. So I just want to make that very clear. The third hypothesis that was supported across all sites sought to compare differences in peak growing season, median EVI values. So as I discussed back in point one, the growing season values are highest or should be higher at a freshwater site just due to the fact that those canopy species are not being impacted by saltwater intrusion. So they're not having to expend some of their energy and potentially shed leaves because of that stress, leading to higher primary productivity, in turn higher EVI values, whereas trees that are experiencing saltwater intrusion will have diminished values during the growing season. And this is another place where this hypothesis was not supported at the Louisiana site. And as I discussed on the first hypothesis, there's differences, the differences in the distribution or the EVI values that we saw at this site were different than what we would expect to happen ecologically, given the known stressors that the downstream site is experiencing. And I discussed the kind of unique ecological and hydrologic setting of Southeast Louisiana that may be, that may explain why we got the results that we got here. And finally, the last hypothesis that was supported across all four sites, or was supported the best across all four sites, was comparing the ratio of the growing to dormant season across each site. So at a freshwater site, if you have an EVI value of 2, for example, during the growing season and 1 during the dormant season, that ratio is going to be 2. However, because of the stress of saltwater intrusion at a downstream saltwater intruded site, your EVI value is going to be lower during the growing season. So let's say that's 1. And during the dormant season, your EVI value is going to be inflated compared to a non-saltwater intruded site. So let's say it's 1.5. That value is clearly much lower than 1, which means that the ratio of the growing to dormant season is going to be lower at a saltwater intruded site compared to a site that is not experiencing saltwater intrusion. So this hypothesis was able to be supported across 3 to 4 sites. And in the one site where this wasn't supported was in the Neches River area. And it's important to note for this particular location, there was an extreme drought in Texas during the middle of our period of record. So the MODIS data set that I use starts in the year 2000, and I used it all the way until 2018. During the middle of that period of record, there was a 500-year drought that the vast majority of Texas experienced, which included a lot of rivers drying up. And on the Neches River in particular, salinity in the river reached 15 parts per thousand during a period, which is 7 times greater than what these trees are used to experiencing. Following that drought, widespread tree mortality was documented in the area. And it's also important to note that the Neches River is hydrologically managed for anthropogenic uses. So this is a picture that we showed before. This picture was taken in 2017, but a lot of dead trees are ever present in the canals and tributaries of the Neches River that we go into. And as I mentioned, there's drought. So if you look at this time series, the red line is the downstream site and the blue line is the upstream site. You can see that the time series kind of match each other on a year-to-year basis prior to the drought, which is represented by this black line. So the high values are pretty similar and the low values are pretty similar. However, after we experience the drought, you can see that the EVI values at the upstream site remain the same over time, whereas at the downstream site, the growing season EVI values take a sharp decline. And so having this type of change in the pattern of our data set may have influenced the way that these statistical tests were executed and ultimately the result that we receive. And this structure here is part of that hydrologic management of the Neches River. So this is a structure that they call the saltwater barrier. My sites are downstream of this. During periods of low discharge, low river flow, they close these gates, these locks, and stop fresh water from moving down the river. And they do that to create a freshwater dam basically behind this barrier and prevent saltwater from moving further up, because there's a reservoir several miles up the river in this area that they don't want to be contaminated. However, because these trees are now facing stress from saltwater ingressing up the river, whatever fresh water is coming through helps to alleviate that stress. But because there's no fresh water moving through once these gates are closed, now the stress that those trees are experiencing is even worse than it would be given the situation at hand. So just to recall the differences in EVI values that we expected. So the distribution for a freshwater site we expect to be bimodal and generally skewed right, whereas or not skewed right, but the EVI value should be higher, the median EVI value, compared to the distribution of a downstream site, which should be unimodal and have lower EVI values. In an average year, the growing season EVI values will be elevated compared to the growing season EVI values of a downstream site. And the reverse is true during the dormant season, with EVI values being elevated at the downstream site compared to the upstream site. And finally, long-term trends. In general, you'd expect EVI values to decline for some time at a saltwater intruded swamp compared to a non-saltwater intruded swamp. And so just as validation of these conceptual ideas, what I did was pool all the saltwater intruded sites together. So all 4 saltwater intruded sites were averaged to produce this red line in each figure. And the blue line represents the average of all upstream sites. So you can see from that conceptual understanding, this is actually validated by the real world, where the freshwater site has a bimodal distribution with, on average, higher median EVI values. And the downstream site, though it doesn't have a unimodal distribution just yet, you can see that the peaks of this distribution are closer together than the peaks of the upstream site distribution, which for me says over time, these peaks may start to merge into a unimodal distribution. In an average year, you can see the differences that distributions have with respect to one another over time. So these black lines demarcate the growing season that I used, which was April to June. EVI values, the peak growing season EVI values were higher than the peak growing season EVI values between the 2 sites. And during the dormant season, the hierarchy of those values switched. And then looking at long-term trends, you can see that on a year-to-year basis, the growing season for EVI value, growing season EVI was higher at the upstream sites on a year-to-year basis compared to downstream sites. And the dormant season EVI values were lower at upstream sites compared to the downstream sites on a year-to-year basis. So this pooling validates my initial conceptual understanding of this phenomenon. So that's important to know for me moving forward as I start to kind of tweak this to get out some of the kinks. So there are some technical and methodological considerations. One has to do with the period of record of MODIS. So MODIS only started in the year 2000. And we have an understanding that unless the saltwater intrusion is very acute, it may take a while for the ecological effects that we see to materialize and become detectable using remote sensing. Whereas Landsat, which Landsat with red, green, and blue bands started in 1985. So that's a 25 or a 20-year head start on MODIS in terms of the in terms of how many images they have of an area. However, there's a difference in the sampling rate of MODIS and Landsat. So an important step for me is to get an understanding of how often you need imagery to accurately reconstruct a time series to use for these statistical tests. In addition, having a data set that has a smaller pixel size. So in MODIS, the pixel size that I use is 500 meters compared to Landsat, which is 30 meters. So having a smaller pixel size will allow us to pick areas that are maybe more obscure and not as large. And we don't have a lot of large swamps left. A lot of them are very much a patchwork. So we would be able to examine these kind of patchwork swamps compared to looking for areas where we have large continuous swamps, which, as I said, are fairly rare at this point. And in addition, in order for me to really interpret these results, I had to have a lot of local knowledge to contextualize them. So at the moment, this type of approach is most applicable where you have on-the-ground knowledge and understanding of what's been happening for several years ecologically, which there's just some areas where people haven't done any research. We may have some inference, but we don't have any hard figures to talk concretely and make contextual inference based on that to use for our remote sensing analysis. So back to the take-home messages, remote sensing data can be used to identify chronic low-level saltwater stress sites and coastal floodplain swamps. This work is ecologically motivated, or the hypotheses are ecologically motivated. Some are better supported across sites than others. And as I said, because these hypotheses mostly are the ones that were most supported, looked or were able to differentiate based upon bulk parameters, based upon summary statistics, that indicates that the outcome of saltwater intrusion, so lower primary productivity and stress, those are easier to detect than the process of saltwater intrusion. So the trends that I talked about, which the hypotheses based on trends were not supported more than 75% of the time, those indicate that detecting the process of saltwater intrusion is more challenging using the methods that I proposed and executed. So the next steps is to kind of start to map swamps and their health. So this is a quick classification that I did where blue is represented by, or water is represented by blue, red or marsh is represented by red, yellow are unhealthy coastal floodplain swamps, and green are healthy coastal floodplain swamps. So I hope to take this type of classification scheme and extend it beyond just my research area so we can start to visually map very quickly the health of swamps and get a more dynamic understanding of saltwater intrusion and the effect on swamps. So that's all for my presentation. If you have any questions, we have a Q&A section.
Okay. Thank you very much, Elliot.
Yeah, thank you.
I'm going to direct participants' questions.
Mm-hmm.
If you can allow me to share my screen as
I can do
well.
that.
And let me see where I am. Okay. Current slide. Here we are. What I want everyone to know that if you haven't had a chance or haven't thought of a question or it's going to come to mind after we get off the out of the webinar today, you can have, or you can of course email your question directly to Elliot, and his contact information is shown on this slide, of course. So, Elliot, the first question that came up was, why did you choose to use MODIS as your data set?
Yes, so that was something I had to wrangle with, but because I didn't know how frequently I needed images, so as I said, Landsat has a return period of every 16 days to the same location. MODIS is every 1 to 2 days. And so although I understand that the period of record for MODIS is much shorter than Landsat, I wanted to optimize the period of return so that I had enough data to actually run these tests. So that was kind of the deciding factor, was how many images I could get over a certain period of time.
All right. I did want the viewing audience to know that Elliot, he's a gator, and he worked on the Swanee River at some sites that were set up for our agency, the Swanee River Water Management District, by the USGS 20 years ago. And Elliot is just as highly motivated as those researchers were a generation ago. And I'm really looking forward to picking your brain in the future, because I know you're going to be doing a lot more. And I'm not going to hog this question and answer session, but I wanted to give you a fair warning on that, Elliot. Plus, very interested in what you've done in Big Bend as well. So okay. I have a question. Mm-hmm. Hello from Peru. I have a hardware question. How powerful does the computer need to be to properly process images?
That's a question I don't have an answer for, because as I pointed out, I use Google Earth Engine for this. So Google Earth Engine is all internet based. So there's a website, you can just Google Earth Engine. You can sign up for it, and if you like do any remote sensing on that platform, none of it's done locally. So you don't have to download anything from NASA or the USGS. They have many of those data sets available to you at call. So you can write the code and call certain images. And then when you execute your code, it goes to the Google server. So Google Earth Engine is a cloud computing platform. So as I said, nothing is run locally. You run everything on their hardware, and then they send you back the results. So the advantage of that is that you can do some pretty complex things and you can get your results back pretty quickly. I haven't used ArcGIS or ENVI or any of those platforms before, so I can't truly compare the speed of them. But just from talking to colleagues who have used those systems, I've heard that like people have set up something to run overnight, they came back and it crashed or something like that. So you lose several hours of productivity, whereas with Google Earth Engine, as I said, the reason I started to use it was because I was teaching myself remote sensing and I need to learn from my mistakes very quickly so I didn't waste any time. So I would write up some code that I thought would work and would get the job done, send it in. A minute later, I'd get back something saying like, this just doesn't work for XYZ reason, rewrite the code, rerun it, and then get results back. And so depending on the complexity of your code and what you're asking their servers to do, it may take a longer time, but the longest I think I've ever had something processed on their servers was 20 minutes. And that was for like something fairly complex. So if you're just starting out with remote sensing, I would, I guess, push you to that so you can get an understanding of the different data products and how to use them very quickly. So yeah, for what I did, I could have done this on my phone, to be honest, because nothing is being run locally. Everything is done through cloud computing.
Wow. So when I get off of this, I'm going to be ready to go to WildNote app and Google Earth Engine. So, I have another question. Do you think there might be other remote sensing methods that would be able to better demonstrate the process of salinity intrusion?
Yeah, that's something that I've been racking my head about. And I think one thing is just to have a longer period of record. So as I mentioned, Landsat with 3 bands. So you need 3 bands for EVI because it uses the red, green, and blue bands. Landsat goes back to 1985 with those 3. So if we have a longer period of record, the slope may become more significant because you have a longer change over time. So that may be something that we can do without changing the methods, just changing the data source. But in terms of methodology, I think we just have to be more specific about how the process of saltwater intrusion is represented on the landscape, and then how you pick those up using simple remote sensing methods. So when I first started this, as I said, I knew nothing about remote sensing, and now because I'm in a postdoc where all I'm doing is remote sensing, I'm learning a lot more than I did before. And one data source that may be particularly of use is radar data. So Sentinel-1 has radar information, the synthetic aperture radar. And with radar information, you're able to get structural information, not just optical reflectance information. So we know that swamps, for example, the structure of those systems change as a result of saltwater intrusion. So you go from a canopy that is fully leafed out during a portion of the year. Over time, you get a canopy that eventually will have no leaves. So the structural and reflectance patterns from radar may change more drastically than the optical patterns, or the color patterns will change. So looking at the time series of structure from radar information may be more telling than the time series information that we get from optical information. Now, the drawback of that, unfortunately, is that the freely available radar information that comes from Sentinel, and their satellite went up in 2015. So that period of record is extremely short compared to optical data sets like Landsat and MODIS. So I think radar information is very promising, but I think the period of record makes it challenging for me to accurately represent what can be done with that type of information.
All right. All right. Well, I'm going to have time for one more question, then I'm going to have to wrap up the webinar. So hopefully this will be a short one. It's actually a long question, so let me if I can get this out right. I've noticed similar stress in areas with modified and increased hydrology by levees, berms, roads, etc. Do you believe the remote sensing and EVI methods are sensitive enough to differentiate between effects of prolonged ponding versus saltwater intrusion, or is that where local knowledge is needed? Would you like me to repeat that at all? Any of that?
Yeah, I was definitely going to say, no, I got it. That's definitely where local knowledge is needed. So if you read the literature, at times people note that it's really hard to know whether the stress that they're seeing is due to long-term impoundment, or if the stress is due to the salinity of the water, because the effects on the trees can be very similar. So, I mean, one way that you could do it on the ground to differentiate is by taking salinity, pore water salinity from the trees. So seeing like what's the concentration of salinity going up their xylem, or taking salt concentration from the leaves. So that's a way to differentiate between those stresses. From remote sensing, it may be a little harder. There's some indication that you can use microwave radiation in order to detect differences in leaf stress. So a leaf that's stressed from saltwater intrusion might have a different reflectance from microwave radiation due to salt crystals, compared to a site that's just stressed from permanent or semi-permanent pounding, because those leaves won't have an increase in salt concentration. They may have a decrease in some other parameters like different nutrient concentrations, because they're not opening up, they're not moving as much water through their roots as normal. But yeah, I think I'll leave it there before I start word vomiting.
All right, Elliot. Man, thanks so much. This has been great.
I appreciate the opportunity.
All right, man. So for our next webinar is actually in June. We don't usually have a June webinar, but due to the fact that the Society is not going to have an annual meeting this year, well, we were able to sneak this one in. And we're going to have Edward D. Enspinger from Mississippi State, who will be presenting his work on the effects of disturbance and elevation on wetlands of Mississippi roadside rights-of-ways. Should be very interesting. And also, our next Spanish webinar will be held on June 24th. It will be presented by Brigitte van Tussenbroek and Ricardo Wong from the National Autonomous University of Mexico, speaking about zoobenthophylae. As a reminder, all the Spanish webinars are offered free of charge to members and non-members alike. And finally, be sure to subscribe or follow SWS social media channels like Facebook and LinkedIn to keep informed and support the Society. We also have a YouTube channel, I mentioned earlier, where all our webinars are posted 3 months after their original broadcast with multilingual subtitles and newly added or wetland interviews, one in English and one in Spanish, posted on our YouTube page. You can quickly link to those on the SWS website under the Resources tab and select Wetland Interviews. If you're Spanish speaking, be certain to subscribe to the Latin American and Caribbean region's Facebook page at the link listed here. Once again, Elliot, thanks for your presentation, and everyone, please have a wonderful day and stay well.
Thank you very much.
All right.